So today, Frank will talk about light shaping from a physical optics perspective. So we already see your presentation, Frank. We already see you. So
good.
Go ahead. Good luck.
Okay, great. Thank you very much for the introduction, Yuri, and also for the invitation to this talk. It's my pleasure to talk here. And yes, we come now to a physical optics understanding. I can say you that there is a lot of overlap in the mathematics in details when you go into details, which is maybe not so obvious in my talk, but I can see that easily. I like to say that this talk is in particular also based on two PhD students' work, Liangxing Yang and 𝗣𝗵𝘆𝗀𝗵𝗆, who are doing work on this shaping, and 𝗣𝗵𝘆𝗀𝗆 in particular on spline techniques in optics, spline interpolation techniques in optics. So I'd like to mention this. That's the structure of my talk. I don't go through these topics here. I do it step by step anyway. But I like to mention that the demonstrations I do in this talk are all done with our software virtual fusion. And I like also to mention that though we do physical optics, the simulation time in all the cases is about a few seconds. So it's not a long simulation time. Okay, let's start when we talk about physical optics, let's start to say what is the object we are dealing with in physical optics. And that's a light representation. And in physical optics, we describe light, of course, by electric field, the magnetic field also we have, of course, but in optics, we typically don't talk about it too much. So we have the electric field with three field components, and which is very, very important in this talk, because it's also related to the optical path, in fact, is that we always can extract a common smooth phase factor from the three components. That is not an approximation or something, it's just a form of representing the complex field, right? So we have a common phase. That doesn't mean here is no phase anymore. There's still a phase, but there is a common phase, wavefront phase, I call it. I'd like to give you an example. Let's consider a Laguerre-Gaussian beam and with some aberrations. Okay, and then the amplitude is clear. That's a donut. The vortex is the phase which belongs still to the U field. And then, of course, we have the smooth wavefront phase, which is typically not 2 pi modulo, and which is also in our algorithms, it's represented another way. So the U field and the wavefront phase are represented in different ways in the mathematics, in the code, in the software. Okay, so that's what we apply. And now let's talk about first about light transformation or field transformation. By the way, the company is Light Trends because we are liking to do light transformations. Good. So if we do a light transformation in physical optics, we think we have an input field. So now we have this E in, and we have the U field and the wavefront phase. And then we are looking for some kind of components or system to transform that in some output field. This is a single field problem. The multi-field problem is based on that. I have no time to talk about this in this talk. I just give an example at the end. Okay, so I concentrate on the single field. And the question is, of course, how to achieve a transformation with sufficient accuracy. And in optics, we typically try to achieve that by manipulating the wavefront phase. That is what we talked about. Both speakers also before. Manipulating the wavefront phase is exactly the way to try to do it. And here is a very, very simple example. It's a focusing lens, right? A focusing lens problem. So I have an input plane wave here for on axis, so angle is 0. And I like to focus it, so I like to have a spherical output field. So plane wave to spherical output field. Then what do we need to do? That's obvious. Here in this plane, we need to introduce some kind of wavefront phase response, which is just the difference of the two ones in this plane. That's easy. Okay, so it's obvious to do. And I like to say it, here we have a phase matching. It means we have an input phase and we have an output phase. And in one plane, they should fit to each other. And if something is missing, then it's a wavefront phase response. It's very close related to the discussion of optical path length and so on. Okay, so that's just the description in phase terms directly. Then, of course, in the next step, if we like to design, so that's a very typical thinking, which comes a little bit from diffractive optics. That first we are asking the question, what kind of phase do we need to introduce? And then we ask the question, how to do that in practice. That means how to come from the delta psi to one or more surfaces. Yeah, and that can be done by freeform, by Fresnel zone surfaces, by diffractive optical elements, here, diffractive lenses in this example, also meta surfaces. And there are more examples, volume gratings, etc., etc. That means we have different ways to implement a surface or a structure on a surface, a flat optic surface, which is implementing this delta psi. So we have always two questions, delta psi, and then how to do it. I have no time in this talk to talk about how we implement these surfaces. I can just like to say that we can do that. Okay, and that means if you know the delta psi, we can calculate the surfaces. I give you examples. I cannot talk about how we do it. That means it's all about the control of the wavefront phase. I give you one example for this lens. So here we have a numerical aperture of 0.4 for the focusing lens, and we have calculated from the simple wavefront response we know. We have calculated here, for example, two interlaced aspherical surfaces to obtain a little bit flatter lens. To have two segments. And you can do a ray tracing simulation of this to get a perfect spot. And you can do also field tracing, that is our physical optics modeling, to get the point spread function and the MTF. Okay, so the MTF, the gray one is the ideal one, and the black one is the simulated one. So it's a full simulation of the situation. Okay, so that means these are things we can do. And if we know the delta psi, then we are in a good situation. Okay, so let's come to light shaping as a part of light transformation. And let's consider this example, a beam expander, very simple thing. But you see here, the domains of the input beam and the output beam, they don't fit. So here a wavefront phase is not enough, obviously not. So what we need to do here is we need also what I call a domain and irradiance matching. It means the domains of two beams must match somewhere. And to have energy conservation, the irradiances should be matched. So, and for a beam expander, we all know how to do that. We introduce another element. This element is first getting the aperture, the diameter, and then we do a collimation with the second one. And here I'm very much where Olivier started, that we need two elements, one for shaping, one for the phase control. He also said that. And so that means here we are exactly in this. We need one element where irradiance shaping in this plane, and then we need a wavefront phase control in this plane. By the way, I like to mention that this kind of general concept, it's a very general concept, was, in my opinion, already suggested by 𝗤𝗵𝘆𝗀𝗵𝗆. He also was a professor in Jena, is now retired. In 1985, he called it a tandem component, one for shaping, one for controlling the phase. But he did it in a paraxial world, so it was not in the non-paraxial world. Now, I'll give you an example, a full example. Let's consider the incoupling of a laser diode with a strong astigmatism into a fiber, single mode fiber. Here we need to transform, light transformation, the laser diode with astigmatism into a single Gaussian beam here. Here we need a perfect Gaussian beam in the waist to have an overlap integral to get a high coupling efficiency. Now, let's discuss it, what it means. It means that we first need to do a light shaping, and then we need to do a focusing. And the input comes from the laser diode. The output comes from, we need a Gaussian beam of the diameter, which is given by the core of the fiber. Now, let's do it. Here, it's the picture of the input beam. It's very astigmatism. I think that's millimeters here even, that's micrometers. Then we propagate it a little bit. Then we get this beam here in this plane. In this plane, we like to do the focusing. That means in this plane, we need a Gaussian amplitude or irradiance. So it means from here to here, we need a shaping from a Gaussian to this, from this one to a Gaussian. So we need a shaping phase here. Let's do it. We design it. I come back to this, how we do that. And then we get here in this plane a perfect Gaussian profile, but of course the wrong phase. Then we control the phase, and then we get a perfect focus, and we get a coupling efficiency of 99%. That was a functional design, so just the phases. And now we use our techniques to calculate a free-form surface from the phases, and then we get this result. That means we have here our two free-form surfaces and get an efficiency of 98%. So this is a full workflow, which is not using any kind of parametric optimization. We just go through it, right? And we just need to fix some parameters, and then we can calculate that. So that is what we do here. And so that means the shaping step is super, super important. And it's not only important for light transformation as a part of it, but as was discussed before, of course, also as an application itself, for example, in lighting or in non-imaging optics in general. So now the question is, what kind of delta psi shape we need to introduce here? If we know it, then we can calculate the freeform surface, then we can calculate the HOE, we can calculate the meta surface, whatever we like. So, but that's the question. Before I come to the design, I come now to the modeling. So how to model this light shaping scenario? So how to model that in physical optics terms? Let's do it. It's very simple. We do it what we call a field tracing diagram. So in physical optics, we are always switching between the X domain and the K domain. That's very, very normal. So let's start with the input field. Then we do just a multiplication now with this phase we are looking for. We don't know it now, so we multiply it when we know it. Then we do a Fourier transform. Then we do the propagation in the K domain. That is just a rigorous propagation kernel in physical optics. And then we do a back Fourier transform, and that's it. That's all, okay? By this, we have the full physical optics modeling. We can do it for all components, no problem. And it's important to understand from a mathematical point of view that the first step is a pointwise operation. That means we have coordinates here and we have coordinates here. So it's not an integral operation, it's a pointwise operation. This multiplication, obviously also, it's a pointwise operation in the K domain. These are just functions which are multiplied, right? By the way, that does not change when we go to the structure. So if we model in physical optics a smooth surface, it's still a pointwise operation. I just like to mention that. Good. So that means if these are two pointwise operations here, then the major question is, what's with the Fourier transform? And the Fourier transform, of course, is in general an integral operation. So it's an integral operation, and so that is exactly, it looks a bit like Huygens principle, and a little bit it's like that, right? So if we consider this a little bit more, in particular, when we apply the stationary phase concept to the Fourier integral itself, then it can be shown that the Fourier transform can approximate it by a pointwise operation if the wavefront phase is strong enough. And here is a paper where we published this, and that means that's a pure mathematical approximation. That means the mathematics teach us that the Fourier transform becomes a pointwise operation in some situations where the wavefront phase is strong. And now we apply this mathematical approximation, not a physical approximation. Now we apply this mathematical approximation to physical optics modeling. That means we ask the question, what does it mean if the Fourier transform and maybe also the inverse Fourier transform becomes pointwise? Okay, let's assume both Fourier transforms would be pointwise. Let's assume that. Then it's obvious that the whole transformation from the input to the output becomes a pointwise operation, because all four operations are pointwise. And that is a very, very important situation, because then it's obvious I can also replace my pointwise operations by just one pointwise operation from the input to the output. And all the information how to do it is given by the whole mathematics. So I can formulate it. We can formulate a pointwise operation in the X domain, full in the X domain. That gives us a clear indication that this is exactly the theoretical and practical connection to ray optical modeling and design. That means this shows you when a physical optics modeling becomes on the basis of a pure mathematical argumentation, not a physical argumentation. On the pure mathematical argumentation, the physical optics modeling itself becomes pointwise. And that also shows us that physical optics includes a ray optics consideration in an accessible way in form of a unified algorithm. And that's exactly what we use. And so I don't go into the X domain, but we stay because the physical optics formulation enables a seamless transition between the pointwise and an integral approach. So I stay in this formulation. And now for the rest of my talk, I like to concentrate on the far field light shaping. Because if I go here to the far field, then it can be shown that then the inverse Fourier transform is pointwise. It's even the specified pointwise one. So it means then this Fourier transform is pointwise. And the only question is, what is with this Fourier transform? That means everything is about this Fourier transform. If this Fourier transform is a diffraction is important, then it is an integral. If it's not important, if a diffraction is negligible, it's a pointwise one. And this decision follows from the parameters of the modeling and design task. It follows not by assuming something, it follows. And I'm just finishing a paper which is called Generalized Fresnel Number by Relative Diffractive Power, which generalizes the Fresnel number concept to discuss that in detail. And it's very, very nice because it's directly related to Fresnel numbers, but in a more general way. Anyway, that means the design and modeling task gives me the answer if this is a pointwise Fourier transform or not. Let's consider an example. Let's consider an example that's a preview to the designs. Okay, so I do now a design. I'll explain later how to do that. That means let's consider the two scenarios. One, it's a very non-pixel scenario, plane wave in, small collimated beam in, and here irradiance out, and here a little bit less non-pixel, right? It's still not pixel, in fact, but a little bit less. Good. Now I do a design assuming a pointwise Fourier transform. I say later how we do that. Assuming a pointwise Fourier transform. I assume a pointwise Fourier transform. Then I get these results as a height profile of my surfaces. So I calculate the surfaces and get that. Then I apply the B operator. That is, the B operator is the modeling of the surface itself. It includes the Fresnel effects, and you can see it here. So there are some amplitude modulations here. This is quite strong, 1.3 to 0.8. In the other case, it's very, very small, right? So 9695. Then I do the Fourier transform. And now I assume first a pointwise Fourier transform. I assume it, so I enforce it. And then I see in the Fourier domain, it looks like what I like to get maybe. So it looks like this. And because I assumed a pointwise Fourier transform in the design. And now I switch over to the integral Fourier transform. And then you see here, nothing happens. And here you get a strong effect. So it's blurred. You have diffraction effects here at the corners. In the Fourier domain, you already see it. And if you now go to the irradiance in the target plane, so now we are here, then you see easily that there is a problem. So that means, which is very nice, that just by switching the Fourier transform, it's a very easy process in modeling. You can get a full pointwise modeling, a super fast one, or still a very fast one with the integral Fourier transform because of FFT. And in our software, we have an automatic selection of the Fourier transform type. You even don't need to care about it. Our software is doing it automatically. Or you can do it, of course, customized and enforce things when you like. Good. Now let's come to a typical thing in physical optics, which is called the Fourier transform algorithm. And I like to show you how this is related to the mapping type approach in design now. Now I come to the design. Let's consider now our far field light shaping situation. We can consider any kind of shaping situation, but I like to stay here in this talk in the far field light shaping situation. So that means, let's consider the functional design. Functional design means the input field is given, the irradiance of the output is given, and we are looking for the phase which we need to introduce to do the shaping. If you know the phase, you can calculate the elements. Okay, now, let's assume we have a Gaussian input. Let's assume we like to have a top hat in the output. Very typical question. Then we can now, because we have a pointwise connection here, we can invert this. So we can calculate from this, we can calculate the constraint in the Fourier domain. This is a constraint in the Fourier domain, which follows from here. It's a non-Parexel situation, so that's deformed here. Okay, so that means, you see, in the far-field light shaping, we can forget all of this here. So we can completely concentrate on this, because this follows from the irradiance. That's a one-to-one calculation, including the polarization is a little bit tricky, but it can be done. So we can do it for unpolarized light, for polarized light, that's possible. Good. Now you see what is remaining. Remaining is we have an input Gaussian beam, and we have this constraint from the amplitude in the Fourier domain. Yeah, that means the functional design of the phase response now is nothing else than the Fourier pair synthesis. We have here a Fourier pair, and we need to synthesize this Fourier pair by finding this phase. It's a very, very well-known problem, which was discussed in diffractive optics very, very much in the past. And the result was, in diffractive optics, to do that, was the iterative Fourier transform algorithm. It's a projection type algorithm. That means we introduce constraints in the X domain and constraints in the K domain, and then we do an iteration there are several ways to do that. So there are different versions of that, but it's all the same idea. Constraints in both domains, and then by that to find the phase which is doing the job. This algorithm was introduced in diffractive optics, but it's not absolutely not restricted to diffractive optics, not at all. It's a very general mathematical concept. It's a little bit based on a fixed point iteration in mathematics. It's a general approach. So let's apply it to our example. Now I take here a Gaussian input field, and I like to have the 𝗟𝗵𝗴. I take 𝗟𝗵𝗴 here in Jena, of course, the Gaussian input field to 𝗟𝗵𝗴 picture here in a quite non-Parexel situation. Now let's do it. Let's do the iterative Fourier transform algorithm. So that are my constraints now. So I calculate first from the irradiance, I calculate my constraint. That looks like this. And then now I can apply my Fourier transform algorithm to apply it. So I take my input field. Then I need to have an initial phase. It's very, very often a very good choice is a spherical phase, which is doing at least the bandwidth. So then I go to here, Fourier transform. It looks already quite like a mapping style. We come to this very soon. Then I apply this constraint and replace this by this. And then I go back. And I do it with an integral Fourier transform, so no approximations. And now you see already, there's a problem. Here it's a mapping style, here's a mapping style. And if you investigate it even more, you see, in this case, the phases are identical. Or in short, the iterative Fourier transform algorithm doesn't work. It stagnates. The reason is because, in fact, the Fourier transform starts to behave like a pointwise mapping. That means the question is, if you have this kind of situation, which is a non-Parexel situation, where the IFTA is not applied in the past, to say it this way, we have a stagnation problem. And the question is how to overcome this stagnation problem, or to say it differently, how to overcome the stagnation problem when the pointwise Fourier transform is allowed. Okay, and how to do this? Yeah, we have a good information that's very much related to the conservation of flux. It's a Parseval's theorem in Fourier pairs. And we can formulate it like this. And if you assume a pointwise transformation, then we know that this kappa and rho have a mapping relationship. And if you have a mapping relationship, voila, we are there where my speakers before also were, in particular the last one. We are in the Ampere problem, in the optical mass transport problem. So we come to the Jacobian determinants and all this stuff. So we do a transformation here. So it means we come to the same problem or the same issues as in array mapping in the X domain. But we are doing it in the Fourier domain, because we like to stay in the concept of physical optics and Fourier pair synthesis, because we think that is more general and more elegant as a piece in a bigger context. So we apply now this same techniques, but for this problem, Parseval's theorem. And if we do that, then we get also a coordinate transformation. So we get the meshes, and we get a coordinate transformation. And from this coordinate transformation, kappa of rho, we can now calculate the phase. Why can we do that? And I saw this equation also in the talk before, because from the point-wise Fourier transform, we know there is a relationship between the phase of the output field here and the relationship to the k-domain. And now we can calculate the antiderivative of this equation. We also know the OMT result is integrable gradient. So we know that here. And then we get the delta psi shape. So by this way, we can calculate that. And here's an example. So we take this source, then we calculate the phase. That's a phase here. I take the spherical part away. So these are the aberrations, because we need to introduce aberrations in light shaping, of course. And then we get a very, very nice result for the simulated irradiance here with the full Fourier transform, the full physical optics modeling. That means we come to the following resulting workflow, which we follow. First, we conclude the Fourier domain constraint from the irradiance in the target plane. Then we assume first a point-wise Fourier transform and synthesize the Fourier pair by the mapping type approach, as I discussed before. Then we check the modeling with the integral Fourier transform, if that's accurate enough. If accurate enough, we are ready. If not, then we continue with the IFTA to further optimize the Fourier pair, including the diffraction effects. And then we have, at the end, we have the delta psi shape. Then we can calculate our freeform surface, our HOE, our meta surface, or whatever we like to do. That's a structural design. We had already an example where the modeling of the integral Fourier transform gave a problem. That was in this example here. So that means here we can now take our next step. We continue with the IFTA. And let's do it. So we start with our OMT result. Then we need to wrap it, because the IFTA itself is working, unfortunately, with the 2-pi modulo technique, because FFT is involved. That's an issue, which is still to be considered, how to calculate then, how to unwrap it again, by the way, and what happens there and so on. But anyway, so we use the IFTA, and then we get a slightly changed one, which can also be unwrapped, of course. And then if you see the result, so that was before the optimization, that is after the optimization. So it means this works very, very nicely here. I like to show you at the end of the talk 2 more examples. This is an example where we use the full workflow. So here we have a plane wave again, a collimated beam, X-polarized, and we calculate a full freeform component to get this specified irradiance. And then we calculate it. So here it's a freeform surface. My colleague called it a lens. So let's call it a lens. So here we have a lens. And then we get here the simulated irradiance of the full thing. I like to emphasize this includes all effects, polarization effects, Fresnel effects. And it's not only that the Fresnel effects are included in the modeling, the Fresnel effects are even included in the design, which is in a non-pixel modeling quite important. Okay, and you can also see that the Fresnel effects are, of course, a little bit polarization dependent. Here, not too much. If it would be more non-pixel, then much more. But here, just a little bit. So I like to show you. No, I have not. I have skipped that. So here, the last example, because I like to show you an example with 2 input fields. Here's a VCSEL source now, 1000 nanometer X-polarized. But it is a multimode source. So we model the irradiance in the far field of the input field. We model by 2 modes, 2 LG modes, Laguerre-Gaussian modes. And we take these 2 Gaussian modes, and then we design the freeform component. And here you see the result. That's a freeform surface. Here again, the height profile. And we get a very, very nice simulated irradiance, again, including all effects, polarization, Fresnel effects, diffraction, everything included. And I like to show you also here the polarization dependency. It was designed for X-polarized light. Then you get a nice, quite nice profile here. And if you take to Y-polarized light, you see a slight difference. That's clear because it was designed including the polarization. And then you have an effect, which if you have a very non-pixel situation, it becomes, of course, more drastic. Okay, I come to the conclusion. I hope I could show that the physical optics formulation of light transformation and the light shaping provides a deep insight on how the pointwise, which is related to ray optics, and the integral, which is related to diffractive techniques, are connected. They are connected, in fact, just over a mathematical decision of the Fourier transform. This is more and more in our concepts and our software that is implemented. That means we have a very seamless transition between ray optics and physical optics. Of course, we always do physical optics, but this pointwise can be, if you strip all the fields, if you put the fields away and just consider the optical paths and maybe the fluxes, then you are in ray optics. If the physical optics modeling is pure pointwise, if it's not pure pointwise, of course, then ray optics is wrong. But we can still do it, and it's just a seamless transition of the software. The pointwise Fourier transform is a key technique for this unification. And if you do integral Fourier transforms and pointwise Fourier transform in your algorithm, as we do it also in our software, that requires quite some sophisticated sampling techniques. So we have typically hybrid sampling. So we use equidistant Nyquist sampling for part of the field, and spline interpolation and Zernike fitting techniques for other parts of the field. So we have a hybrid sampling concept. And you also saw, and I have shown that the mapping type approach and the IFTA Fourier pair synthesis they both do Fourier pair synthesis in our approach here, and they are working together. The IFTA stagnates where the mapping type approach works well, and the IFTA can take over when the mapping type approach is not accurate enough because diffraction matters, and that gives a quite nice workflow in light shaping. And the modeling is already completely included in virtual fusion, and the design, the mapping type IFTA is also included, of course. The mapping type approach is now added step by step this year and the beginning of next year. Okay, thank you very much for your attention.